Chapter 20. Many electron atoms. Section 20.5. The Hartree-Fock self-consistent field method. For a many electron atom, the Schrödinger equation can be solved iteratively and approximately using the self-consistent field method proposed by Hartree and Fock. For example, the Schrödinger equation of the helium atom is this: H psi equals E psi. H consists of kinetic energy operators for electron 1 and electron 2, the attraction felt by electron 1 and electron 2, and the repulsion between the two electrons. We neglect the kinetic energy of the nucleus because it's much smaller than the kinetic energy of the electrons. And also, later we will see it's possible to recover the kinetic energy of all nuclei in a system in a different way. This is the Laplacian for electron 1, Laplacian for electron 2 in polar spherical coordinates. R12 is the distance between electron 1 and electron 2. It's the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And this term is really difficult to deal with. There's no easy way to separate the coordinates from electron 1 of electron 1 from the coordinates of electron 2 in this expression, 1 over the distance between electron 1 and electron 2. Therefore, we have to make approximations to simplify this Schrödinger equation for the helium atom. And the essence of the Hartree-Fock self-consistent field method is to break the Schrödinger equation of two electrons into two simpler Schrödinger equations, each containing only one electron. So we're about to just solve one electron Schrödinger equations. What if we have many electrons? Well, we will just break the Schrödinger equation of many electrons into many one electron equations and solve those one electron equations first, and then finally come up with a solution to the Schrödinger equation of many electrons approximately. This is just because it's much easier to solve one electron Schrödinger equations than to solve a Schrödinger equation of many electrons. The Schrödinger equation for the helium atom is this: H psi equals E psi. H is the Hamiltonian. The Hamiltonian consists of the kinetic energy operators for both the electrons, the attraction felt by both the electrons, and the repulsion between the two electrons. This can be simplified to two Schrödinger equations. This two. In the first Schrödinger equation, it contains only electron 1. In the second Schrödinger equation, it contains only electron 2. Therefore, these two equations are one electron Schrödinger equations. In principle, we can always solve those one electron Schrödinger equations. But what is this? Well, V sub 1 effective. This is the effective potential energy felt by electron 1. And this is the effective potential energy felt by electron 2. So in these two equations, somehow we have to propose the effective potential energy for electron 1 here and for electron 2 in the second equation. Phi 1 is the wave function for electron 1. Phi 2 is the wave function for electron 2. Epsilon 1 is the energy of electron 1. Epsilon 2 is the energy of electron 2. And also we call epsilon 1 and epsilon 2 as atomic orbital energies. Phi 1 and Phi 2 are called one electron atomic orbitals because Phi 1 contains the coordinates only of electron 1. Phi 2 contains only the coordinates of electron 2. Now really, these two, the effective potential energy operator, they are both one electron operators that contain the coordinates of only one electron. So V1 effective contains the coordinates of only electron 1, V2 contains only coordinates of electron 2. But then first, how can we make the effective potential energy operator of electron 1 not contain the coordinates of electron 2 and vice versa? So that's question 1. And 2, well, how to determine the expressions of the effective potential energy operator for this 2? We will resort to quantum mechanical postulate 4. So in postulate 4, we learned how to get the expectation value of a physical property. But this time, we're not going to get a value. We're not going to get a expectation value. We will get a expectation potential energy operator. We'll get the effective potential energy operator. So over here, the effective potential energy is the sum of the attraction and repulsion, and given the total wave function psi of 1 and 2, we can somehow evaluate the repulsion operator of the 2 electron repulsion. Here, this is our approximation. We can just integrate the total wave function. This means complex conjugate. So this is the complex conjugate of the total wave function of the 2 electrons. And over here, we apply the repulsion energy operator to the psi, the total wave function. And d tau is the volume element. But look, before we used to have d tau to be the volume element of both electrons. But here, we're going to have this d tau be the volume element of a single electron. Here's the idea. For electron 1, the 1 electron effective potential energy operator may be expressed as this. Alright, this is effective potential energy, and over here we have attraction. This is simple. But then what about electron-electron repulsion? Doesn't that include the coordinates of electron 2? Yes. However, we can integrate this psi star and then repulsion operator applied to psi, and then d tau 2. Over here, d tau 2 is the volume element of electron 2. And if we integrate over the coordinates of electron 2, we will be able to effectively remove the coordinates of electron 2 using this integral. Alright, for example, let me give you an example. If we integrate xy with respect to dx, and x is from 1 to 2, the final result will not contain any x, right? So if you integrate x times y with respect to dx, x is from 1 to 2, I think you will get 1/2 x squared times y, and x is from 1 to 2, and then you will get something like 1.5y as the result of that integral. So by integrating this 2 electron function with respect to the coordinates of electron 2, you remove the coordinates of electron 2 in the final result. The final result will still contain the coordinates of electron 1. So that's the idea. For electron 2, we do similar things. The effective potential energy of electron 2 is the attraction it feels from the nucleus, plus over here we integrate psi star, repulsion operator applied to psi. Now with respect to d tau 1, d tau 1 is the volume element of electron 1. So now we have 2 effective potential energy operators for electron 1 and for electron 2. And over here, it contains only electron 1. This operator contains only electron 2. And by the way, this psi should be the total wave function of the 2 electron system. The total wave function can be built up in a format of determinant. In this case, it's 1 over the square root of 2 factorial, the normalization factor over here, and a 2 by 2 determinant. You have electron 1 in the first row, electron 2 in the second row. phi 1 in the first column, phi 2 in the second column. It's a 2x2 determinant to ensure that this wave function is anti-symmetric under the exchange of 2 electrons. But here's another problem. So I was assuming that we know this psi 1 2 to derive the expressions for the effective potential energy operators. We do need to know psi 1 2 here, 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 and here to somehow express the effective potential energy operator for electron 1 and that for electron 2. And we know how to build this total wave function of 2 electrons. Alright, it's just this determinant with this normalization factor. And phi 1 and phi 2 are normalized wave functions. Phi 1 and phi 2 should be orthogonal to each other. So we know all that. But what are the expressions of phi 1 and phi 2? Shouldn't we solve the one electron shorting equation for electron 1 to get phi 1? And then solve the one electron shorting equation for electron 2 to get phi 2? Well, somehow we cannot do that because we do not even know what are the effective potential energy operator for electron 1 or for electron 2. Now we're stuck. Unless we know there exists some kind of iterative algorithms designed to solve this kind of problems. So here is this iterative algorithm. In general, you can use similar algorithms to solve many mathematical problems. Over here, we're going to just use this mechanism to solve the shorting equation. Step number 1. Make an educated guess of phi 1 and phi 2 to construct the total wave function psi 1 2. So over here, this is going to be just a pure guess based on some understanding of the 2 electrons. So it's not really a pure guess, it's educated guess. For the helium atom, I think I would guess phi 1 to be e to the power of negative 2r multiplied by alpha. Phi 2 would be e to the power of negative 2r multiplied by beta. So it's some kind of guess based on the nuclear charge. Because the nuclear charge is 2, I'm just guessing it's a exponential function e to the power of negative 2r. And we know one electron should be alpha, the other wave function, the other one electron wave function should be beta, something like that. So that's going to be my guess. And based on the educated guess of phi 1 and phi 2, I can build psi 1 2. Once we have psi 1 2, we'll use quantum mechanical postulate 4 to obtain the effective potential energy operators of V1 effective and V2 effective. So we just use this postulate 4 and we integrate psi star. So this is psi star, and then the repulsion operator applied to psi. But when we integrate this integral, make sure for the effective potential energy for electron 1, you integrate that integral with respect to electron 2 only. And to get this, you integrate with respect to electron 1 only. That way, V1 effective and V2 effective are not going to be some numerical values. V1 effective will be a function of R1. V2 effective will be a function of R2. And now we can use V1 effective and the kinetic energy operator for electron 1 to construct a one electron shorting equation to obtain phi 1. We'll use V2 effective to build a one electron shorting equation for phi 2, and we'll solve for phi 2. And now we get phi 1 and phi 2. The phi 1 and phi 2 here are different from our initial guess of phi 1 and phi 2. And then we simply use the new phi 1 and phi 2 to get a new total wave function psi 1, 2. And after we get a new psi 1, 2, we get a new V1 effective, a new V2 effective. And then we use the updated V1 V2 effective to obtain another updated set of phi 1 and phi 2. From the latest phi 1 phi 2, we build another psi 1, 2. We keep repeating steps 2, 3, 4 until the convergence of the effective potential energy operator for electron 1 and that for electron 2. And that's called self-consistent field. This is how we solve the Schrodinger equation for the helium atom that contains 2 electrons using the self-consistent field method proposed by Hartree and Fock. For the lithium atom with 3 electrons, for the 118 electron atom with this many electrons, or even a very large protein molecule that contains 500,000 electrons, we use a similar iterative algorithm. Alright, if you have 118 electrons, you can write a single Schrodinger equation that contains 118 electrons. But then we need to break this huge Schrodinger equation into 1 electron Schrodinger equations. How many of those? 118 of those. In each 1 electron Schrodinger equation, you need a 1 electron effective potential energy operator, and you can solve that 1 electron Schrodinger equation. Then you get phi 1, phi 2, phi 3, all the way to phi sub 118. And using all those phi's, you can build a determinant to get the total wave function of 118 electrons. And using that total wave function, you get the new set of effective potential energy operators. So we repeat those steps from step 2 to step 4 to keep updating phi 1 and phi 2, to keep updating psi of all electrons, and to keep updating the effective potential energy operators until the convergence is reached. So that's the idea of the self-consistent field method proposed by Hartree and Fock.